Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about stress strain diagram. So this is the stress strain diagram under tension. So how we draw the stress strain diagram? First we take a prismatic bar, then we will subject it to tensile load using a machine called universal testing machine. This machine is universal testing machine. Using this machine, we apply a tensile load on the prismatic bar. So first we apply some value of tensile load, then we gradually increase the load. Gradually increase the load. So from increasing load, we will get what is the value of stress at that point of time. And from that, we can find out the value of strain using a extensometer. This is a extensometer which is connected to the prismatic bar, which measures strain. Okay. So we plot this stress and strain. Stress we are increasing gradually. So on drawing this graph, for a ductile material, we get the graph something like this. So now we are going to understand these different regions we got from this graph. Okay. So this will measure the strain. So if you enlarge the views here, actually the rod which we take will be look something like this. So it is prismatic in this region, right? Prismatic in this region. But at edges, the cross-sectional area is more. Why we provide like this? Because here we are applying the point tensile load, right? So we already know that in this region, there will be non-uniform distribution. Okay? Non-uniform distribution of stress. That means stress concentration, right? So because of that, the stress will be more as compared to the prismatic region. But in the region where there is uniform stress distribution, the maximum stress in the non-uniform distribution will be more. So there may be chances of rod failing here, but we don't want that. So we increase the area. So although you increase the load, but load per unit area is the stress, right? As that area is more, so we can ensure that the rod will not fail here. That will fail in this prismatic region. Understood? So that is the reason why we provide like this. So we only consider this length L. This is what we know called as gauge length. Okay, this is gauge length. So actually there are two types of material. One is ductile materials which show ductile behavior. Another is brittle behavior. They are brittle materials. What is the difference between these two that we understand later? So first we understand that using universal testing machine, the rod will be subjected to a tensile load. So from that the rod we will increase the tensile load gradually. So we are increasing the tensile load gradually. So we need to define a term called rate of loading. So per second, how much rate of loading you are applying? That is known as rate of loading. So gradually we increase the load and we find out the stress and strain. We draw the graph. So for a ductile material, the graph will be like this. So this is the ultimate stress. After this stress, the material will fail. So let us first understand region OB. Okay. Region OB, you see region OB. This is region OB. So region OB is elastic region. Elastic region means once you remove the load, the rod will regain its original shape and size through the same path. So means, see, as you are increasing the stress, the strain is increasing, the material is getting deformed in this direction, right? But once you remove the load, the material again will compress to get its original shape. So the deformation which is caused by the tensile load, if you remove that load, that deformation will be recovered. Okay. So that is about elastic region. So deformations. One more thing is that deformations are generally less. Why, that we know later. Deformations are less, and recover deformations on removing the load, i.e. gains its original shape and size. Okay. In this, there can be two types. See, if you see, it can be linear, can be linearly elastic, can be non-linearly elastic. Okay. So now let us discuss about region OA. So if you see region OA में जो भी elastic, see we know that O to B is the elastic region. In that region OA is linearly elastic, means this part OA is linearly elastic and AB is non-linearly elastic. So this diagram is not to scale diagram because the actual stripe line here that will be very near to the y-axis. That we understand through an example. Suppose let us take the steel. Steel is a ductile material. So the value of modulus of elasticity for steel is 200 into 10 cube megapascals. So this is Hooke's law region. So we can apply sigma is equals to E into epsilon. So E will be is equals to, see in this region what is slope? Slope is y is equals to mx. So this will be sigma, this is E. So m will be is equals to E. What is m? M is tan theta. Tan theta is equals to E. So theta is equals to tan inverse E. So as sigma is in megapascals and strain is unitless, so we need to substitute the value of E in megapascals, right? So we need to substitute theta is equals to tan inverse of 2 lakhs. Whoa. So let us find out what is the value of theta. So shift tan inverse of 2 lakhs. So that is the value of theta is 89.99714 degrees. So from this is the angle theta. That theta is 89 point, means that is nearly 90, right? Nearly 90 degrees. So it is nearly attaching to the y-axis. So suppose, see if you see the yield stress here, the yield stress is nearly something, right? 260, right? Then what will be the value of strain? Strain will be 260 divided by E. That will be strain, right? So that will be 260 divided by 2 into 10 power 5. So that is 130. So that will give us 13 into 10 power minus 4. So this is the strain, means very less strain. So in this elastic Upsilon region, the deformations are very small. So that is the reason why we generally design the materials or elements, design the civil engineering elements in elastic region, because the deformations will be very small. Once the load disappears, they will regain their shape. Suppose it is it gone beyond the elastic region, then the deformations will become permanent. So they will suppose the beam is like this. After deformation, beam become like this. Then after removal of load, the beam will look like this. Then do you feel comfortable? No. You think that it is about to fail, but actually it is not failing. But you think like that. So because of comfortableness in thinking, so human psychology is like that. So because of that, we generally design these structures in elastic region. Okay. So this is about the graph. This is scale graph. You can scale this. So region OA is Hooke's law region. So now one question, Hooke's law is valid for. The Hooke's law is valid for option A, all elastic materials. Only for linear elastic materials. Only for non-linear elastic region materials. D, none of this. So what will you say? The answer will be linearly elastic. So Hooke's law, sigma is equals to E into epsilon. So sigma is y-axis, E into epsilon is x-axis. For a homogeneous and isotropic materials, E value is constant. So y is equals to mx, a straight line. So this is linearly elastic material. This happens only in the case of linearly elastic. Happens only in linearly elastic region. Okay. So Hooke's law is valid only for linearly elastic materials. It is not valid for all elastic materials. So, for example, if you consider steel, if you see its stress strain diagram, sigma epsilon, initially it will have a straight line. Okay. After that, it will change. If you consider rubber, in elastic region, this stress strain diagram is something like this. It is also elastic. Both are elastic. Okay. But this is non-linearly elastic. This will be linearly elastic. Right? So iska sigma is equals to E into epsilon. If you, this should be sigma is equals to E into epsilon power n. You can say like this, right? Right? So with this we end today's lecture. In next lecture we are going to discuss more concepts on this part. Until then, take care. Bye bye from 9 pointer. Thank you.